Welcome to The Explainer. Today, we're diving straight into the fascinating mathematics of making optimal decisions when, well, you just don't have all the facts. Imagine you're forced to make choices continuously, but the only real way to figure out the best choice is to risk making a few bad ones along the way. So, how do you balance that desire to learn with the desire to win? That's exactly the puzzle we're exploring today. Okay, let's quickly run through our roadmap. We'll kick things off with the multi-armed bandit problem. Define and minimize regret, and then check out 3 key strategies: epsilon greedy, UCB, and Thompson sampling. Finally, we'll wrap up with some real-world applications. Section 1, the multi-armed bandit problem. We're starting our journey with a really foundational concept in reinforcement learning and sequential decision-making. Picture yourself walking onto a noisy casino floor. You're faced with this long row of slot machines, or as statisticians affectionately call them, arms. Now, each one of these has a secret, completely unknown probability of paying out. You've got a bucket of tokens in your hand and a limited amount of time. If you play a machine and win, do you stay right there? Or, do you try the machine next to it, which might just have an even higher payout rate? So the crucial point here is balancing that totally natural urge to stick with a winning machine against the curiosity to try an untested one. This is famously known as the explore-exploit trade-off. Think about it. If you strictly exploit your current knowledge, you might just get stuck on a machine that pays out moderately, and you completely miss the jackpot machine sitting right next to it. But on the flip side, if you spend all your time exploring every single machine, you're literally wasting valuable tokens on duds. You need a mathematically sound strategy. And I absolutely love this quote because it brilliantly illustrates just how mathematically infuriating this problem was when Allied scientists first tackled it during World War II. The multi-armed bandit problem was so incredibly intractable to statisticians at the time that mathematician Peter Whittle actually joked it should be weaponized to distract enemy scientists. It sounds like a simple casino game, right? But mathematically optimizing that explore-exploit trade-off is a massive, massive challenge. Moving into Section 2, defining and minimizing regret. To solve this impossible puzzle, mathematicians needed a clear metric to measure failure. Now, what's really fascinating here is how this translates a deeply human emotion into a simple, cold, mathematical formula that we want to minimize over time. Regret, in this context, is simply the difference between the reward you would have received if you had played the absolute best machine every single time and the reward you actually got. Over hundreds of rounds, every single time you pull a suboptimal lever just to explore, you accumulate regret. The ultimate goal of any bandit algorithm is to ensure that as time goes on, your average regret per round drops all the way down to 0. Section 3, epsilon greedy, random exploration. Let's take a look at our first algorithmic gambler and see how it tries to minimize this regret using a pretty simple coin flip heuristic. The epsilon greedy strategy is one of the earliest and honestly most straightforward solutions out there. It essentially splits its time. For the vast majority of your polls, let's say 90% of the time, you act greedily and exploit the machine that has the highest known payout based on your history. But for that remaining tiny fixed fraction, our epsilon, say 10%, you just pick a machine completely at random. Now, while this is incredibly simple to implement, the fatal flaw here is that a constant exploration rate forces the algorithm to waste time exploring forever. Even after you've confidently found the absolute best option and played it 1,000 times, epsilon greedy will blindly force you to pull a bad lever 10% of the time. Because of this endless random wandering, the algorithm suffers from what we call linear cumulative regret. Your regret just keeps growing on a straight upward trajectory forever, no way around it. Which brings us to Section 4, UCB, or optimistic frequentist bounds. To fix the endless random wandering of epsilon greedy, we need to introduce a much more calculated gambler. UCB, which stands for upper confidence bound, operates entirely on this incredibly elegant optimistic principle: optimism in the face of uncertainty. Instead of just looking at the average payout of a machine, UCB calculates a margin of error. It basically assumes the absolute best possible outcome for any machine within that mathematical margin. It actively gives the benefit of the doubt to the unknown. Here's how it actually plays out on that casino floor. For every machine, UCB calculates an optimistic upper bound. If you haven't played a machine in a while, its uncertainty bound naturally grows larger and larger. Eventually, that optimistic bound gets so high that the algorithm is essentially forced to pull it. But the real magic happens when you do pull it. As more data is gathered, that uncertainty envelope automatically shrinks. So unlike epsilon greedy's infinite wanderings, UCB naturally slows down its exploration as it learns. Because of this, it achieves a logarithmic regret bound. meaning your regret actually flattens out over time rather than climbing forever. Huge improvement. Next up, Section 5, Thompson sampling, Bayesian beliefs. Let's see how this builds into our third and most sophisticated strategy, which was actually first theorized all the way back in 1933.
Thompson sampling takes a totally different Bayesian approach. Instead of calculating a hard mathematical upper bound like UCB does, it maintains a fluid probability distribution. Think of it as a belief about each machine's true payout. You start with a prior belief. You pull an arm. If you win, you shift that whole distribution higher. If you lose, you shift it lower. Before every single pull, the algorithm samples a random guess from each machine's current probability curve and simply picks the highest one. And as you get more data, those curves concentrate really tightly around the true payout.
Finally, Section 6, Real-World Bandit Applications. Now that we've met our 3 algorithmic gamblers, it's time to leave the theoretical casino behind. Comparing these key strategies side by side answers the crucial question of how we actually minimize regret in practice. Contrast epsilon greedy with the others. It relies on rigid, blind randomness, resulting in infinite linear regret. It just doesn't learn when to stop. UCB improves on this massively. Using frequentist optimism, it limits regret by calculating hard statistical bounds, dynamically shrinking exploration as it gets smarter. And then Thompson sampling provides this highly sophisticated Bayesian alternative. By updating probability distributions rather than hard bounds, it naturally and elegantly balances exploration and exploitation without needing manual tuning. It really is a clear evolution of logic across these 3 methods.
But you might be wondering, why does minimizing this regret matter so much in the real world? Well, the stakes dramatically shift when the arms are pulling aren't just slot machines, but experimental drug dosages given to actual human patients. In phase 1 and 2 clinical trials, researchers are literally running a multi-armed bandit algorithm. They desperately need to find the most effective treatment dosage without giving a patient something too toxic or completely ineffective. And these algorithms adapt to context too. We call these contextual bandits. By framing contextual data, like patient health profiles or even your daily web reading habits, bandit algorithms adaptively learn the optimal treatment or recommendation. For example, a variant called LinUCB was famously deployed by Yahoo News to instantly match articles to readers based on real-time features. It didn't just find the single most popular article for everyone, it found the absolute best article for you, actively minimizing the regret of a missed click. And this whole journey leaves us with a profound ethical question about machine learning, especially in critical fields like healthcare. When we optimize for regret, how do we value the cost of learning the truth? Sure, it's super easy to tolerate a 10% random exploration rate when you're just losing plastic tokens in a slot machine. But when exploring a suboptimal arm means giving a patient a less effective drug just to gather statistical data, the math suddenly takes on a very heavy moral weight. Understanding these algorithms isn't just about math anymore, it's absolutely crucial for understanding how machines make decisions on our behalf. Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you next time.